All right. It's really great and honorable to stand in front of many great scholars. And I also know many people are very tired, so I'll try to make it as fast as possible. But unfortunately, my slides are composed of 3 sub-parts, so I cannot guarantee, but I'll try. My slides is actually less technical compared to other talks. And it's more conceptual. And actually, I heard many people were talking about resilience yesterday, but not today. So today, I think it is a good time to talk about something else other than networks. But still, I'll try to make a linkage between the concept of resilience and complex networks too. At the first part, I will talk about resilience in general, but not in detail though. So what is resilience? Many people are asking the meaning of the resilience, how to apply it, right? Since 1970s, when C.S. Hongik, who is a great ecologist, have published a paper about the stability and resilience in ecological systems. The use of the concept and the meaning of this resilience has been dramatically increased since then. Not only in the ecological field, but in diverse fields, including economy or engineering, climate change sciences, or disaster management. But, well, there was always a problem for directly applying this concept and meaning to each specific field. So still, there are many papers that are coming out talking about what is resilience, how can you use it. And I and my colleagues, including Suresh Rao, also contributed to make this more complex. But anyway, well, although it is very important to find out the real meaning and the real methodologies that we can apply, but these days what I'm trying to do is to go back to the original meaning, which was first suggested by C.S. Hongik. And well, here we are looking at 2 types of the systems, the ecological systems. The one system is about the coral reef system, and this figure shows very different types of the response, or their states. And the second example is about the water table of the groundwater. Well, this water table also experiences the regime shift because of the change of the condition. The key point of this example is that there is a multi-stability in this system. So there is a stable state, but once it experiences the regime shift, the shifted state also remains as very stable. So the key point is there is a multiple stable states. So then why those kind of multiple stable states exist? Well, because there is a nonlinearity and threshold effect, hysteresis. Well, we prefer to deal with the systems to have this kind of response. But if we are to deal with the complex systems, well, sometimes they behave in this way. So, however, when people are dealing with the resilience in engineered systems, what they really focus is the speed of recovery instead of the existence of the multiple stable states. The existence of the multi-stability means that the resilience of the system is not about how fast it can recover. It's about the recoverability, whether the system can recover from the alternative stable state to the original state. However, in engineered systems, people are assuming that there's only single stable state, and it's only the matter of time whether the system can be recovered or not. But is it really true? Is the engineered systems always have only single stable regime? Well, let's think about the example of Fukushima. In 2011, there was a nuclear power plant explosion, and I think it will take 2 or 3 decades to become that system to be calm. to the original state? And then would you interpret it as the regime shift? Or do you think it's not a regime shift, but it will only take a very long time to recover? Well, I see this as the regime shift. So I look at the engineered systems, complex engineered systems, to have the multiple stable states as well. So what I argue is that we need both for the recoverability and the faster recovery, since, well, people are relying on the engineered systems and they want to have the normal life as fast as they can after they get disturbances. So in our work, what we suggested was the resilience of the complex engineered system is actually an emergent phenomena that emerges from this kind of processes, and we call it resilience processes, and this includes the sensing, anticipation, adaptation, and learning. Well, we can match each of these single processes to each of these stages, but well, it is not limited. Well, they can go to plan and prepare stage and also to the adapt and learning stages. What I want to say is that instead of looking at only this stage when people are concerning about the speed of recovery, well, these stages are all related to all of these phases. And based on, well, depending on what they do in, for example, at the planning and preparing stage, for example, well, people are doing very well for sensing and anticipation during this planning stage. Well, the path after getting the disturbances will be very different. Well, if they're doing well, this path will be like this, and if they don't do well, well, the path will look like this. And sometimes the final recovery state will be not same as the original one, and sometimes it will be below it. And I will see this as the regime shift too. So this is the idea why I'm saying the resilience is the emergent property. Now, I also want to say, well, sometimes the topological features that we observe from the complex networks is also the emergent properties. And if we can make the relation between that topological properties to the resilience of the system, well, then that means also the resilience is also the emergent properties of the complex networks. To the people who are working on the complex networks, well, these figures are very famous ones. These networks are two extreme cases for the complex networks. So one is called random and the other one is called scale-free. The biggest difference between these two is the node degree distribution, as you can see here. The random networks node degree distribution is like a Poisson distribution. And the other one, the scale-free node degree distribution, follows the power function. And the biggest feature between these two is the range of the value for the node degree. Well, while you can have only limited range for these networks, well, these networks allows to have a very big range of the values for the node degree. Sometimes it expands to several orders of magnitude. And also, because of these topological features, their responses to the attacks or disturbances are also different. Briefly speaking, the scale-free network is, in general, more doing better job when they are attacked in a random way. However, if they get attacked in a specific way, based on their importance, like the degree centrality or between the centrality, they were evaluated to be more vulnerable. Although this kind of structural responses does not tell the full aspect of the resilience of the system, but well, still we can get some idea from this kind of results. So I and my students also, well, many people already saw these figures yesterday a couple of times. I and my students are working on the string networks and also grid networks, and these are the 4 regions in Korea. We selected these regions based on the age, actually, after the development stage. So this Sejong city is only like 2 or 3 years old now, while this Ilsan, Gangnam, Eunpyeong in this direction, well, we can say they are older and older. So what we assumed is that the cities will self-organize, and the self-organization will produce the emergent properties in their topology, which becomes like scale-free networks. So we analyzed their nodal degrees, and while these three regions showed the scale-free properties in their topology, well, this one showed the exponential distribution. So in this x-axis, the scale is in log, while this is in normal scale. Well, the differences in the response of these networks are more emphasized if we look at the response by measuring the efficiency of the network. So it looks like the Sejong city, which is the youngest one, is less vulnerable when they get the specific attack, not the random attack. Well, also when it is done by the betweenness centrality, it also shows the similar results. Also, we look at the grid networks in Korea. Well, since there were no other networks that we can compare to assess how vulnerable these networks can be, so we generated artificially the random networks, scale-free networks, based on their size. We chose the similar number of nodes and also the similar value for the average node degree. And then we generated and compared with these two, with this one. What we expected was, well, there are several studies that tells the power grid, the node degree of the power grid is not actually scale-free, but it is close to the exponential distribution. So our Korean networks also exhibits as exponential. Well, it means it's closer to the random network instead of the scale-free network. The interesting thing is, well, this power grid was always vulnerable to the random attack and the specific attacks. So it's not, well, so the degree distribution is not the only one that can tell about the vulnerability or the resilience of the networks, but there must be some other metrics, additional metrics that has to be analyzed to conclude or to interpret these results. But anyway, as I said, well, resilience is not just the response of the complex networks when the nodes are simply removed. What I'm interested is what happens when we try to recover this network. Well, sometimes it will fall. Well, after the collapse, sometimes it can fully recover, and sometimes it cannot. So the additional feature that I want to suggest, especially to my students and also to other people who are interested in, is the addition of the multi-stability, the characteristic of the multi-stability in these complex networks. The one way is to put that multi-stability characteristic into the nodes. And if these nodes are attacked, not just simply removed, well, they can move into the alternative regime, which simply can be interpreted as the removal. And sometimes, well, they just stop the function temporarily, and they can do the same function as before when some time passes, right? So that's one idea. And also, another element that has to be added, which is now studied by Daniel Eisenberg, over there, is that we need to consider the human elements when we are dealing with the infrastructure networks. The infrastructures, especially which were built by the hard material, well, they don't have the adaptability by themselves. It is the human elements who makes them to be adaptive, right, and flexible. So This is one kind of elements that we want to add, and that's what Daniel is trying to do. So what I'm suggesting is that at least these two elements, the multi-stability and the human elements into the networks, should be considered when we are dealing with the resilience of the networks. Now I'll go on to the part 3. And I'll briefly introduce the recent study that I and my student have done. This is not directly related to the complex networks. However, after looking at the talks from other scholars, well, these are very relevant to the networks, although I haven't done it. We'll see what it means. What I did for this research, what I and my student did for this research, was to look at the response of the streams to the change of the urbanization. So it's about the coupled complex systems. So I'm looking at the response of a complex system, which is coupled to the other complex system. Barter et al. In 2013, he published a paper which shows there are two types of flow regimes by analyzing numerous watersheds in USA and Italy. Well, this can be distinguished by space or by the characteristics of other features such as topographies or climates. Well, one regime can change also temporarily to the other regime by the change of the features, the landscape features. So that was the one thing that we want to observe. So what we did was to look at the urbanization ratio in Korea in 78 unit watersheds distributed all over the country, which are located also in these 5 major river basins. And first we looked at the urbanization in each of these watersheds. Well, this is the probability distribution of the urbanization. Most of the watersheds had very low urbanized land area, while there were a few number of watersheds that has very high urbanization area. And then, well, before we go this, and then the idea was, the methodology that I used was to do the spectral analysis from the time series of the stream flow. And then by using those fast Fourier transform technique, what we get is the noise in the frequency domain. And if you look at the slope of the noise, it will tell you the landscape feature, whether the landscape has the ability to store the water, more water, or not. So the idea was the increasing imperviousness due to the urbanization will make the less water to be infiltrated into the subsurface, and the less water will be stored. And then the stream response will be more similar to the rainfall pattern. So this is the result of the spectral analysis, and well, you can get many information from this figure, but the major variable that we are looking at was the average slope of the spectral analysis results. If the slope is close to 1, well, we interpret it as having the persistent memory. So what we expected for the urbanized watersheds was to have the slope which is different from 1. Sometimes go to the 0 or sometimes go close to 2, which means they lose the memory. So this is the results we got, and let's look at only this figure. So over the urbanization, what we observe is that the spectral slope, the average slope, is varying a lot. So the urbanization itself is not the only feature that defines the stream flow of a watershed. There are many other features like topography, climates, slopes, etc. So many other factors actually defines the stream flow characteristic. However, if the urbanization increases, now these values converges and actually converges toward a lower value, which becomes which means that landscape is having lower memory. So these were the results that we got recently. However, well, the further study that I want to do is to link this kind of characteristics to the networks of the drainage networks, right? So we started to collect these drainage networks from several cities, and we want to see what the topological features of these networks would impact the stream flows in the watershed. And I saw that already many people were actually tackling that problems. So I'm hoping to collaborate strongly with them so we can solve the problem more easily than I expected. So this is my concluding remarks. First, I want to emphasize that the existence of multiple attractors is a key feature when we are talking about resilience. And we need both the recoverability and the speed of recovery when managing a network for resilience. And because of the linkage between resilience and emergent network topological features, resilience should also be understood as an emergent property of a complex network. And this is the last slide for my talk. Thank you.